Well, all right. We reached the end of section 10.3, and there's snuck a little calculus in on us. Did you notice? That's what we're going to talk about now. After all that graphing, all those curves we took a look at, we're actually going to start asking calculus-based questions about them. There's three topics. One is the one we're going to do now, which is tangent lines. The second is length of curve, and the third is area. Of the three, area is the most fun. And that's the very last thing we cover in section 4. So let's be patient and get through these other two. It's interesting actually to look at curves like these, but then the question becomes, pick a point somewhere, maybe here, and what happens if I were interested in the rate of change of x with respect to y? How do I get that? It might be important to me. The polar equation does its thing, but then I might want to jump back to so-called rectangular reality and figure out the slope of tangent. Well, there's a way, okay? And it's based upon parametric equations. So what I'll say, the development comes from the following. It says, basically, recall that for parametric equations, and what I'm going to do, let's see if I want to do that or not. Let's call them just x of t, maybe, and y of t. They're functions of t. We have that the derivative with respect to x of y, the rate of change of y with respect to x, we found it to be dy dt divided by dx dt. So that works for parametric. Trouble is, do we have parametric, say, when we're faced with a function that says something like, oh, I don't know, r is equal to, what was that one with the rose curve? Yeah, that was minus 2 sine 3 theta. Minus 2 sine 3 theta. So the question is, what is dy dx? And the answer is, the development does this. They go, recall, also, recall that x can be written as r cosine theta, and y is r sine theta. Believe it or not, those are parametric equations also, because remember, r is some sort of function of theta. So here you go. If you want to find dy dx, you will go dy d theta over dx d theta. Okay, I put an equal sign because that's not enough. Here's a formula that I'm going to give to you, but the way it goes is we're going to derive with respect to theta. I'm so used to x, right? We're going to derive with respect to theta y, which is r sine theta, and downstairs derive with respect to theta x, which is r cosine theta. Now remember, again, r is some sort of function of theta, and so I'm going to leave it as r if you don't mind. And what happens is use the product rule in both cases. We're using the product rule here. One for downstairs and one for upstairs. So this is what we're going to get. We're going to drive r, whatever it is in terms of theta, we're just going to call it r prime. And leave sine alone. Plus, and then we're going to leave r alone and derive sine to get cosine. Downstairs, very similar, r prime cosine theta, but because cosine's derivative is negative sine, it becomes minus r sine theta. That's the development. There's your formula. That's what you use. Okay, so for instance, I can throw an extra one in here if you want me to. I can do this one, but I think what I'll do is I'll go according to the script right now. This is actually a pretty short video. Well, all right. Let's do this guy. I guess I'm getting lazy. If I were to do r is equal to minus 2 sine 3 theta, what I would need in the formula is r prime. So r prime is going to be, can you do that as a chain rule? It's minus 2 cosine 3 theta times 3. How about minus 6 cosine 3 theta? So therefore, dy dx is, you don't have to memorize it. But what you do is you end up going r prime goes here times sine, r prime also here times cosine, plus here minus there, and then it's r times cosine. And I am sneaking a peek up there, and then r times sine. Okay, so what is r? Well, we know what r is. Here are the characters right here. So you get a minus 2 sine 3 theta, minus 2 sine 3 theta, and r prime is minus 6 cosine 3 theta. And minus 6 cosine. That wasn't so hard, Weber. You're lazy. It must be summer's coming. That is, without cleaning it up, that is a formula for the dy dx. Okay? And then you can pick, then the fun begins when you go, yeah, but how about the point where theta is pi over 3? What's the slope there, wherever that point is? And you can go back up to this curve and kind of figure it out. Pi over 3, and I say, oh, is that 0? Right there. Doesn't that, where does that do that? It goes, it's negative. That's a weird curve, isn't it? Okay, it starts at 0, goes negative. So it's doing this loop here. And I'm talking about right there. Maybe there's a slope right there. I'm curious. How about you? Pi over 3. All right, let's do it. So we're going to do another one of these too. Oh, man. Don't have room. So what you would do for that slope is you'd plug in for all the thetas and just plug in pi over 3 and get your answer. That's actually a neat problem, and I kind of wish we were doing that right now. Oh, well. Could have brought that down to here. Here's a new one, though. Nothing against you guys. You're no slouch. Look at this guy. That's a strange-looking thing. Who invented that one? I don't know what's going on there. Find the slope of the tangent. And the next one is, okay, all right, a couple of problems. So, I'm getting a little goofy now, too. So, it says, find the slope of the line tangent to the polar curve, there it is, and when the point when theta is pi over 4, okay? So out there somewhere on the curve is an ordered pair, where theta is pi over 4, and r is, well, you can figure it out if you need it, okay? We don't need it. So, we're going to do this. We're going to go dy dx is r prime. This is y upstairs, so that's going to be sine theta, and downstairs is r prime cosine theta, and then this is plus, and this is minus, and this is r, and this is r, and this is cosine, and this is sine. You could easily memorize this, but I've never forced students to do that. Okay, I just leave it alone. It's fine the way it is. We need to take down r, which is 2 plus sine 3 theta, apparently. I hope this is a good function. I haven't done it. And we need to find also r prime. So the 2 disappears, doesn't it? You derive sine, you get cosine times 3. So it's 3 cosine theta. 3 theta. There you go. Did I make a mistake up here when I derived it? No, we're good, we're good, we're good. Okay, good. So here comes your formula for this guy. You're going to get r prime there, sine theta plus, and r times cosine. And then you switch things. You go, it's r prime again cosine, but then a minus r and sine. You good? So let's plug these guys in. I don't like red. Let's go with U, blue, cool blue. We're going to plug in r prime, which is 3 cosine 3 theta here. And here. This is how it's done, baby. And r is here. 2 plus sine 3 theta. And we're going to right away plug in theta equals pi over 4. And that's going to do it. You're going to find the slope. All right, so I don't bother cleaning up. If I'm going to use it, I just plug the number pi over 4 in. So what I have are 2 angles. I've got cosine 3 theta. Maybe off to the side I'll do this. I also have sine 3 theta. Well, when theta is pi over 4, it becomes cosine of 3 pi over 4. So I'm anticipating plugging numbers in. It's usually, I save ink if I do this, and then sine of 3 pi over 4. Then there's also cosine of pi over 4, etc. So now I'm kind of ready for this. This first guy right here is going to be 3 times. What's cosine of 3 pi over 4? It is a negative radical 2 over 2. What is sine of pi over 4? Radical 2 over 2. Okay. Moving on. Plus 2 plus sine of 3 pi over 4. That guy's radical 2 over 2 positive. Again, this guy's here in the third quadrant, and your calculator might help you out as well. And then theta, pi over 2 is just, or pi over 4 is just radical 2 over 2 there. And then it just kind of repeats. It's 3 times a negative radical 2 over 2. Bit of an alteration. This guy's radical 2 over 2 also. This is a minus, and we've got 2 plus sine again. That's the same thing. It's radical 2 over 2, and then sine radical 2 over 2. So you did it. There it is, whatever that turns out to be. Of course, we want to clean it up because that's how we are. We're good campers. So that's a 2, so that's a 12. No, 2, that's a 2. So that is 3 times 2 is 6 over 4. It's a negative 3 over 2 as it turns out. Plus, I'm going to distribute. I'm going to get radical 2. And then plus, and when those guys meet, it becomes 2 over 4, which is 1/2. Downstairs, very similar. In fact, this is all the same here because of the choice of theta, 3 over 2, choice of pi over 4. And then we have a minus radical 2 and a minus 1/2. Okay. So cleaning up a little bit, let's see what we have. We have a radical 2 minus 1, I think. And then we have a minus radical 2. We've got a, what is this one going to be? That's going to be a minus 2 now. So it's a minus radical 2 minus 2 or something like that. I think that's right. Yeah, I haven't done this, obviously. And so whatever that turns, I'm going to leave it nice and clean and pristine like that. And I'm not going to rationalize the denominator or anything like that. This is not algebra 2. This is calculus 2. All right, one more question, one more problem I'll show you. We've actually done 3. Pretty straightforward formula. There's nothing else to do. Okay, here's a good one too. Find the points. Notice this is the slope. Up here, this is m tan. It is dy dx at that point. That's the rate of change of y with respect to x as this thing swings through the universe, okay? It looks like it is negative. It's a negative guy. Okay. Next one. Find the points on the curve. Here's the curve where the tangent line is horizontal and where it's vertical. So that means m tan is equal to 0 means horizontal, and m tan equal to does not exist or whatever. That means it's a vertical. What I mean by that, you'll see, basically if you divide by 0. Okay, let's see. So we have to find m tan. So let's find this guy's formula. So it's going to be, believe it or not, dy dx is equal to r prime and sine theta, and then plus r cosine theta, and downstairs r prime cosine theta, and then minus r times sine theta. Those sines and cosine thetas, they're there. They're part of the formula, part of the landscape. So we got to do some work. We're going to say, remember, r is 1 minus sine theta. What kind of curve is that one? We'll graph it before we finish here. R prime, the derivative of sine is it's minus cosine. So r prime minus cosine goes there and there. And r, 1 minus sine, goes here, 1 minus sine theta, and again. Now, they're not saying much after that. That's all she wrote. They're not saying plug a number in. Instead, what we're going to do is we have to figure out where it's 0. And the trick to this, you guys, is basically it turns into 2 problems. One, when is this equal to 0, the numerator? That would be horizontal tangent. And 2, when is the bottom equal to 0? That would be vertical tangent. There is an issue where it's horizontal and vertical. What? You'll see. Okay, so let's clean this up. So we've got minus sine cosine. Oops, I wrote it just as I say it. Minus sine theta cosine theta. And saying this one down here is minus cosine squared theta. And here, let's distribute. We're going to go plus cosine theta. And then it's going to be minus sine theta cosine theta. Downstairs we have sine times 1, but it's minus sine theta. And then it's going to be minus sine squared, but subtracted, so plus sine squared theta. Oh, this is a challenging problem. Weber, what are you thinking? Okay, I'll clean up a little bit more. I think I'll clean up as much as I can. Okay, so what I've got is cosine theta upstairs, and then minus 2 sine theta cosine theta. And downstairs, what have we got? We've got sine squared minus cosine squared minus sine. So we have sine squared theta minus cosine squared theta, and then minus sine. Boy, this is an exercise in trigonometry here, baby. Okay, so I'm going to now mentally split this up into two pieces. When is this 0, and then when is this 0, and answer this darn question that I thought I'd be done by now. I'm not. Okay, so the first one's not terrible. You've got cosine theta minus 2 sine theta cosine theta. Well, guess what? Set it equal to 0. Factor out a cosine, yep, and you're left with 1 minus 2 sine theta is equal to 0. So it's saying when is cosine 0 and when is, can you solve that in your head? Put the 1 over and divide. When is sine theta equal to 1/2? Okay. Now, here's the thing. I don't know if the back of the book is saying do you know, multiple angles and all that jive. But if we go for, let's just say, between 0 and 2 pi, that might be interesting. In that case, theta, cosine is 0 at 2 places, at pi over 2 and 3 pi over 2. And sine theta is equal to 1/2 at 2 places, if I think hard. In this case, theta is pi over 6 and 5 pi over 6. That's cool. All right. The other side, not so easy. It has a sine squared theta minus, don't you wish that were a plus? Cosine squared theta minus sine theta. Set it equal to 0. I know how to solve this. I know you guys probably forgot this stuff. Cosine squared can be, oh yeah, that's not hard. You shouldn't forget that. Let's write it as sine squared theta minus sine theta. What am I going to do here? I'm going to go after that identity that says cosine squared is 1 minus sine squared theta. Cool, that's Pythagoras. So we have sine squared theta minus 1 plus sine squared theta minus sine theta is 0. So we have 2 sine squared theta and minus sine theta, and minus 1 is 0. I don't know if you guys get dizzy factoring over trig functions. Okay, but I think this works. It's 2 sine theta and a sine theta and a 1 and a 1, and I want this to be minus and this to be plus. Okay. So the question is, when is sine theta equal to negative 1/2? And the answer is theta is equal to the others 30-degree angles, 7 pi over 6 and 11 pi over 6. And when is sine theta equal to 1? Well, that happens when theta is none other than pi over 2. So it seems like we found it. This is where the horizontal asymptotes, I should say horizontal tangents, are found. And this is where the vertical tangents are found. And you would be happy with that. You might find that you're not quite right, though. Because if we were to graph this thing, it is indeed a cardioid. We've got r is equal to 1 minus sine theta. And I think it does the heart shape, doesn't it? It goes to 1 here and 1 here. And 2 here. Yeah, this thing is doing this number. That's right. It's a cardioid. It's got a cusp. So let's graph what we've got. We've got horizontal asymptotes, or tangents, I keep saying that, at pi over 2. Does it really look like it? Look at pi over 2. But also 3 pi over 2. And that does make sense, doesn't it? And look at a surprise bonus. At 30 degrees, another one, and at 5 pi over 6, another. Those are the horizontal tangents. It fits. That's wonderful. The vertical tangent, 7 pi over 6. So if you go 30 degrees this way, you got a vertical tangent, or 30 degrees this way, another vertical. The real mystery is, look, at pi over 2, you've got both, and it's because it's a cusp. So I think we ought to maybe, I don't know, get rid of that oddity, but be happy with the rest of our answers, okay? That was a good study. I'm glad we did that. That's what the homework, that feels like calculus to me. This is the end of section 3 finally, right? See you in section 4.